morning, everyone. My name is Xing from the University of Osaka in Japan. Today, I would like to talk about my research topic in how we can make the beam from 2D floor plan drawing with the correct dimensions. So I'm not sure about the background of you. So just start from the simple introduction of what is a beam. So basically, when we talking about the digitalization of the building stock, we will say the digital models. Most of the time, this is building information models or beams. So simply, you can just think beam is a 3D geometric model plus the material properties or you also can call it the semantic information. So this technology map places my work within the wider beam reconstruction field. So beam reconstruction mainly include two steps. The first step is data extraction, and the second step is beam reconstruction. And the beam reconstruction is relatively mature and can be handled once the reliable inputs are available. So most of beam reconstruction research focus on the first step, data extraction. And data extraction has many different pathways depending on the data availability. So, and this work focus on the pathway for beam reconstruction from the raster floor plan. And this also called floor plan analysis, and this usually divided into 4 computer vision tasks. They are semantic segmentation, floor plan reconstruction, object detection, and text detection. So each of them has been studied extensively in computer vision community, and the individual performance is impressive. And in the published paper, we review the literature across these 4 computer vision tasks in floor plan analysis. So there are 2 interesting things. So the first one is about the evaluation of the performance. We can see the column there. Most of the evaluation use the metrics such as the IOU or accuracy, F1 score, etc. This metrics is kind of measuring the overlap between the predict result and the ground truth result. And the second thing is that in the text detection task, most of the time the text is treated as noise to be removed. So these 2 interesting things define the 2 research gaps in my work. So the first gap is the dimension gap. So most of the floor plan reconstruction work use a single global scale like this. This is an example. For example, the floor plan spans 10,000 millimeters in 500 pixels. So they will get a global scale of 20 millimeters per pixel. So this has 2 problems. The first one is because the unit of pixel is in integer. There are 1 pixel, 2 pixels, 3 pixels, and there are no 2.5 pixels. So the number, for example, 50 millimeter in this case, could not be represented precisely. And the second thing is that like the raster floor plan, the element has thickness. So there are pixels in thickness. So the global scale will be different even in the same floor plan because the method of measurement is different. And the second gap is about the evaluation. Here are the examples. The first one is the a prediction of semantic segmentation, and the second one is the ground truth data, and the third figure is that overlap them together. Like the white area is ground truth, and the red area is the prediction result, and the yellow area is the perfectly overlapped area. So even like one word is shift a little bit, the IOU is still very high, above 90%. But actually in engineering, there are 8 words in total, and 3 of them, the dimensions are incorrect. So the key idea of my work from a simple observation, like a human engineering looks at the floor plan and we can match the dimension and the corresponding wall. So the key question here is how can a machine do the same matching? Like our scope in this paper is how to use OCR to read the dimension in the paper and match each OCR result to the correct dimension. So here is the workflow. Like we run a fine-tune OCR and directly on the annotated floor plan, reading each dimension in the floor plan, and reconstruct a reference grid. And then we use the OCR result to guide the denoising and conducting semantic segmentation. And finally, we align the semantic map and the reference grid and assign the dimensions to each element in the semantic result. So in this case, every element inherits its dimension directly from the dimension annotation in the floor plan. And to evaluate this at the engineering level, we use IFC. IFC simply is a structured test-based representation of a beam. Like every element can be represented in like a group of mathematical representation. Like in this case, I just transfer all the geometric things into the bottom center line. Like it's just like a vector. It has a start point, end point, and magnitude. So in that paper, we propose three IFC-based metrics. The first one, IFC element, which compare two vectors with a tolerance. The second one is compare the two vectors without tolerance. And the final one is to count the number of like error of counting. So for the evaluation, we use RESPIM dataset. RESPIM dataset is an open dataset which contains more than 1,000 BIM model and the corresponding floor plan. So like I use my method to get the resulted beam and compare with the reference beam and in these three metrics. And this is the quantitative results. So there is a very interesting thing. I also evaluate in the computer vision metrics such as the IOU and the OCR accuracy, and also evaluated in the IFC metrics. So we can see like there is a significantly drop in the accuracy between the IFC and the computer vision metrics. So the interest, like the result from this quantitative, like could be concluded as the pixel level or text level correctness is not sufficient for engineering-oriented beam. And the other is the error propagation. Like in the pixel level, when one wall is shifted, the IOU only affected a little bit. But in engineering, it will affect a lot because when one wall is shifted, the wall adjacent to this wall will also be affected. Let me wrap up. Like we did two things in this paper. First, we just use the OCR, read the dimension directly from the floor plan drawing and attach them to the corresponding elements. So of course there are limitations, like we have a really strong assumption like we need a complete annotated grid, and actually this many real world drawing just don't have this kind of annotation. So in the future research, we could bring in the more drawing types, and but the direction I'm most excited about is the learning-based matching. So let me show you a little bit of my ongoing research. So the idea is to move from the rule-based to learning-based. Like we vectorize the semantic map, so the floor plan becomes a set of line primitive, and the line primitive is just math, like the start point, end point, and the magnitude. The OCR is already structured format too, like the value, orientation, and bounding box. Like once both sides become the mathematical representation, it can become a learnable questions. Okay. If you are also interested in my research area, and yeah, please follow me in my LinkedIn. Yeah, thank you for your attention.